So today I would like to talk about some thoughts on generalization and learning in graph neural networks, which have been used extensively for learning for algorithms. And this is joint work with my student Kyoto, who graduated now, and co-authors from various places. So Jingling, Mochi, Simon, and Kenichi Kawarabayashi. So the algorithms I will be talking about today are probably rather simple from an OR perspective, so more at the level of shortest path or so. But I think many of the observations that we made during these works hold more generally and could be interesting to explore also in other more complicated settings. So with that, let me get started. So when we talk about learning for algorithms, there's various settings in which you can look at this, from learning a full algorithm to learning parts of an algorithm, like a decision within an algorithm, or learning which kind of algorithm you'd want to use, etc., etc. So what I will be talking about today is sort of the aim of end-to-end learning a full algorithm and seeing how far can we get with that. And this algorithm, we will implement it as a neural network. So of course, when you do this, the question is, how well would this actually work? So how well do neural networks in general and graph neural networks more specifically actually learn algorithmic tasks? And what does that depend on how well they do? And of course, that depends on various factors, such as what kind of model you use, the model architecture, the data and the task. What do you actually want to learn? What's the data that you have? And the training algorithm, because that determines what a neural network actually learns. So that's a complex interplay of many different factors, and I'll try to take into account as many of these as possible during my talk. So sort of expanding a little bit. So I'll start with actually an introduction, what is a graph neural network? And then I will talk about two types of results. The first one is thinking about generalization. So in machine learning, that basically means you have your training data and test data come from the same distribution. So you're testing sort of on data that looks similar to your training data and hope that you'll do well. And the second part is about extrapolation. And in extrapolation, what I mean by that is that you look at data that actually looks different from your training data. So in the graph setting, that may be that you're looking at graphs that are larger, that have different degrees, etc. And the question is, what do your neural networks do in that case? So that's an even harder thing to generalize to. So, and we'll see that throughout this talk, this interplay of the model architecture, the task, and the training algorithm and the data actually is going to play a big role. So to start with, let me define what are graph neural networks, because not everyone may be familiar with them. So a graph neural network is a neural network for learning a representation of a graph or an algorithm on a graph. And the way they typically work, or one big class of them works, is that you first learn an embedding of each node by encoding its local neighborhood. And then you collect all those representations and you aggregate it into a graph embedding. And this aggregation could be as simple as just taking a sum or an average, or it could be more complicated. And both of these are operations that you learn. So how do we compute a node embedding? And that's actually already where you see kind of some algorithmic similarities happening. So in a large class of these networks, it's actually a learnable message passing algorithm, essentially. So you start out with each node having a vector representation from the input, and then you go in rounds. And in each round, each node collects the feature vectors of its neighbors and aggregates them by applying a set function over vectors, essentially. And that's a function you're going to learn. And then once you have aggregated that information from the neighbors, you combine it with your own information. And all nodes do this in parallel. And of course, as you go along in the second iteration, you're already collecting information from a two-hop neighborhood, etc., etc. And so what you're learning are really these aggregation and combine operations. So combine is typically just a weighted average. And aggregate is usually parameterized by a small neural network. So you have sort of that little neural network sitting inside, and that's typically just a fully connected neural network in MLP. And this is applied, you apply the same neural network to each neighbor because there's no natural ordering or number of neighbors. So you just apply that same learned MLP to all the neighbors of that node. And you could also take into account some edge features or the center node, etc. So this is message passing. And why do I call this a neural network? Well, it has a neural network inside, but actually here's the bigger structure of this neural network or learned algorithm. So if you unroll this message passing operation here, centered at that target node A. So in the first iteration, A gets input from B, C, and D, its neighbors, and it's computed via this aggregation function, which is this gray box here. So in this talk, I'll usually depict those aggregation functions with gray boxes. And then in the previous iteration before that, B got input from its neighbors, A and C, and likewise the other nodes. So now once you unroll this, it already looks actually like this layered structure. It looks like a neural network, essentially, just that the connectivity is a bit different. The connectivity depends on the graph. And what you have here are essentially these little boxes. So those are actually little neural networks sitting inside there. But you have this layer structure. So now, if we look at this, you could actually think of a graph neural network and many other neural networks actually as some kind of structured arrangement of some learnable boxes. So in this case, these learnable boxes are these MLPs. And this is how we are going to view those networks throughout the talk. So that's just a picture to keep in mind. This is my graph neural network, and you're going to have this kind of computation tree centered and rooted at each node. And they use this shared boxes. So basically within each layer, I could have across the layers, I could have different boxes. Within a layer, I'll have the same box. So now let's get knowing that what a graph neural network is, let's think a little bit about what you can do with a graph neural network, how you can learn with a graph neural network. And in particular, I want to look at generalization and the interplay with the architectural structure of this network. So when we think about generalization, it's basically the question, I have trained this network on some training data, and now I get unseen holdout data essentially from the same distribution. How well will I do? What is the gap between the training performance and this test performance? And that's what I want about. And there has been quite a bit of work thinking about generalization in graph neural networks, the earliest from 2018 using VC dimension, and then some others using more learning theoretic concepts too, like radiometric complexity. Then later on, people started thinking, well, actually for neural networks, also the training algorithm comes into play. So that analysis used the neural tangent kernel to bring the gradient descent into play. And however, sort of the last one is what I want to focus on, is thinking more about the structure of the network and the structure of the talk, which is particularly important when you think about learning algorithms, learning algorithmic tasks, which are very structured procedures that you want to learn. So that's basically the last one. But before we go into the last one, I just want to show you what these learning theoretic bounds, like from the first box, typically look like. So I'll show you some of from our own work. So this is what these generalization bounds typically look at. So these are basically functions. So here there's 3 different settings, and that those little d things, this percolation constant thing depends on essentially Lipschitz constants within the network. So basically some norms of the weight matrices and Lipschitz constants of the nonlinearities. So, but all of them have sort of the similar flavor. They depend on the network depth. They depend on the number of samples. So 1 over root number of samples, it goes down. And then they depend on the inner dimensions and the degree of the graph. So, and the reason I highlighted here this little d is if you basically make this d1, you get the generalization bounds for recurrent neural networks. So graph neural networks and RNNs are actually closely related in that sense. So those are the kinds of bounds we get, and they are useful in many respects. But it's a little bit harder, like, to think about those kinds of bounds when we think about learning full algorithms, because an algorithm, like, what's the complexity of an algorithm, thinking about that, thinking about how it interacts with that model is like a little bit harder to capture with some of these other concepts, let's say. So I want to think about that a little bit more, motivated actually by practical results. So let's take sort of a step further and be a little bit more general in our algorithmic tasks. So here the tasks are what are called algorithmic reasoning tasks. So what these are essentially are tasks like predicting something about relations between objects or next states of a physical system, or for example, computing shortest path, etc. So learning actually algorithms. So in the general sense, you can think of these tasks as you're given a collection of items, a collection of representations of items. You already have those vector representations, and then you do some processing with a neural network to get to an answer to these questions. And this is actually a growing field called this algorithmic reasoning. So now basically we should think about what goes into this gray box. Before even having started thinking about graph neural networks, what should go into this gray box of what should that reasoning network be? So what's the architectural structure of this case? So essentially it has to take as input, in this case, a collection of items, some information possibly about their relations if we have it, and that's it, and output some answer. So there's many ways you can get a neural network on a set of items or a set of vectors, essentially. The simplest case would be just an MLP. That obviously has some drawbacks. For example, in an MLP, it really depends on the order in which I put the items in, and it has to learn that it should be indifferent to the order of the items, because there is no order if I just have a set of nodes or a set of boxes stacked onto each other and I have to predict how they fall. So there is no real order. So we maybe want something that's what's called permutation invariant without having to learn that. So that's an architecture that's called deep sets. It's basically a neural network that implements a set function. So it's basically the order in which you input the items doesn't matter. It treats each of them first individually, sends them through a small neural network, sums up the representations, and then applies another neural network. So this is basically because of the summing, this is indifferent to the order. And then the last thing we can do is we can just make a fully connected graph and apply this graph neural network. And so this is sort of the third thing you could try when learning these reasoning functions over collections of items. And the difference between the graph neural networks and the deep sets is that the graph neural network does more of a pairwise processing and does this like more stage-wise. But from left to right, there's more and more structure in the network, more and more sparsity in the network, essentially. Now, if you think about expressing many of the tasks from the left, from the previous slide, all of these networks are essentially equivalent in representational power, in the sense that if you have some permutation invariant function, so basically a set function over your items, if one of those networks can represent it, the others can also represent it. But if you try to use them in practice, you get big empirical differences. And the reason why people have sort of converged to using these more structured and graph neural networks is the reason that they actually generally work better on these tasks. So now the thing is, okay, that's what we observe in practice. That's what many empirical papers sort of found. And the question is, can we explain this a bit better? Like, can we understand this a bit better? So for that, we have to think about more what we actually want to learn. So now, what do we actually want to learn here? It's more than just a smooth function. It's actually like some kind of function over collections of items, but there is actually more to it. So many of those tasks that I showed as these algorithmic reasoning tasks, like forecasting physical systems, learning a shortest path, or like a graph algorithm or something like that, they're actually the tasks that can be computed by an algorithm, and often actually a dynamic program. So now if we think of an algorithm actually has a lot of inherent structure in it. So you can think of an algorithm also as a structured arrangement of some subroutines, maybe of some for loop, and you apply the same thing, say, to each node in the graph, etc. Now, likewise, your neural network and also graph neural networks, you can think of it as a structured arrangement of some learnable modules. So those are the gray boxes I kept pointing out. And now there's pretty intuitive that sort of if the structures of these two computational procedures match, then the learning should be easier because you've already there's a lot that you don't have to learn essentially that's already implemented in there. So you don't have to mimic a complicated full for loop with an MLP. You actually sort of already have it sort of halfway in there, and you have to only learn small bits of it to adjust to mimic that algorithm. So to make this a little bit clearer, let me just show you one example. So on the left here, you see an algorithm for shortest path. That's the Bellman-Ford algorithm that you probably know. So what it does is it also goes in iterations, and in each iteration, it updates the state of each node, and the state essentially represents the currently best distance that we found to the target. So that update is a very simple update. You just look at the neighbors and see whether there's a better path through the neighbors. Now, if we parallel this with the architecture of a GNN, the GNN also goes in iteration. So each iteration is a layer in the GNN. And in each layer, you do this message passing. You do the message passing update for each node. So you apply this little MLP and you sum it up. So now this already matches. You have sort of a similar for loop over the same things. And now if your MLP, the sum and the MLP, so that's your aggregation function, if that could mimic the update step in the Bellman-Ford algorithm, then you have implemented the Bellman-Ford algorithm and you can compute shortest path. And so now the idea is that all you really have to learn in principle is that your sum and the MLP has to learn a min and a plus over the neighbors, which is a much simpler function to learn than the full algorithm by itself, the full black box. So this kind of idea, we call this algorithmic alignment. So informally, this means that the neural network can mimic a target algorithm via few and easy to learn modules. So basically, we don't want too many of these learnable pieces. And so they can repeat, that's only one piece. And they should be easy to learn. And then we expect that it actually works better with the learning. So let me just illustrate this with the shortest path algorithm as my running example. So here are some empirical results where we try to learn sort of a fancier version of shortest path. And you see, what you see here is the accuracy, so higher is better. And if you look at the MLP, which is on the very right-hand side, and the deep sets, so they don't really have that algorithmic for loop structure that we had with the Bellman-Ford. And they actually generalize very poorly for this task. So even though in principle they can represent it, they may need just more and more and more data to actually do that. So that wasn't enough data. If you use a GNN with one layer, that's also not so good, but sort of starting from 3 to 4 layers, you actually get good learning performance. And this is because you actually have to run enough iterations to mimic that algorithm. And in these graphs, these were relatively small graphs. The shortest path happened to have, in most cases, a length of around 7 or so. So basically 4 is half of the shortest path, and you could do something like a bidirectional Bellman-Ford. So that would explain basically why the GNNs with a sufficient depth actually manage to learn that task, versus the others have trouble. And so maybe they would learn it actually with more and more data. We found that it was really difficult to learn it. So in principle, they can represent it, but they didn't really learn it well. So that's sort of some empirical evidence for this algorithmic alignment. But let me look at this a bit more generally. So basically what you want to do is you want to look at a target algorithm and sort of see your neural network next to it and make this matching of the subroutines essentially. So more generally, many dynamic programs you could actually mimic with this graph neural network if the dynamic programming update would be implemented with this aggregation function. And now many of these algorithmic and physical reasoning tasks actually have this structure, like forecasting in these physical systems, etc., etc. So how can we formalize this? I'd like to formalize this a bit more than just like the intuitive one. So we say that a neural network M epsilon delta aligns with an algorithm if it can mimic this algorithm via now a few network modules. So I have n different network modules, and each of them is learnable with at most m over n samples. So you can think of it as basically all of them together, you would need m samples. That's where the m comes from. And then epsilon and delta comes from PAC learning. So that's basically you learn the function with accuracy epsilon, essentially with a probability of 1 minus delta. And now to actually get these PAC bounds, you can use any analysis technique you want, essentially. So this is sort of like, you can use anything you want. You can use neural tangent kernel. You can use anything else you want. So that's the formalization. And now having this formalization, we actually can show that with some simplifying assumptions that if you have this kind of algorithmic alignment, it actually says something about the learning of the entire task. So basically, if your network and your algorithm align, then you would also learn this task relatively easily. And this is kind of nice. There's of course some simplifications in this theory. So the biggest simplification, I think, is that this essentially assumes some kind of supervision within the layers, which we couldn't get rid of. But in practice, you don't need it. This empirical work actually does something like this. So it really implements this framework, but it holds in practice even without that. So with that, you can show in some cases even gaps between the MLP and the GNN in the upper bounds on generalization. So this is sort of the idea of, well, if the structure of my network and the structure of my target algorithm match in a way, then I can get better generalization. And this is sort of the idea that, well, if I want to do learning for algorithm, I don't start completely with a black box. I actually use algorithmic knowledge and put that in to get a better model. And that's, of course, helps. So I want to continue this idea of algorithmic alignment and sort of the matching of the algorithm and the network. And I would like to take this viewpoint a bit further when thinking about extrapolation. So we saw what helps for generalization empirically and theoretically is if the architecture and the target algorithm match, and basically all you have to learn with your learnable parts is simple functions. So now I would like to take a step further and think about extrapolation. So by extrapolation, I really mean now basically we look at these green data points, which are different, really different from your training distribution. So they are basically out of support for the training distribution. And now we look at the error for such kinds of data points. So it's basically the question, what does your neural network do when you show it data that it hasn't seen before? That's really different from the data it hasn't seen before. So there is no guarantees with a normal generalization for that. But it is the question that people in deep learning actually have been thinking about quite a bit in the recent past. So what does extrapolation mean here? So for example, when you try to learn IQ test, it could mean that you change the shape or the color or the number of the objects. When you think about this physical reasoning, meaning I have like whatever a set of boxes and I see how they're evolving, I have to predict the next state. So once I have learned these interactions and these physical rules, essentially, I would think it extrapolates to different positions, different masses, 5 boxes instead of 4, etc. In graph algorithms, it would mean that if I have learned a graph algorithm, well, if I give the network a larger graph, a graph with different edge weights, with different maybe node features in a different range, like different distances on the edges or something like that, then it should still work because it has learned the algorithm. And similarly for these mathematical symbolic reasoning tasks, different numbers of inputs, etc. So this is something that people have been thinking about, and it's a challenge. So of course, this is out of distribution, so general learning doesn't guarantee anything, and it's challenging to do that. And the key question is, what conditions do I need on the data, on the learning, that this actually works? And I think this is actually important more generally if you think about learning for algorithms, learning for optimization. At what point are you actually within and out of distribution, and how far do you actually generalize? So I would like to focus on graph algorithms, even though what we observe actually sort of it holds for these other tasks as well. Since we are focusing here on algorithms, so these are graph algorithms. So the key question is basically, if I look at graphs that are different from my training graphs, what does my graph neural network predict? Will it still work, or will it not actually run the right algorithm? And now this is something that people have looked at empirically, and they have seen that, okay, it's in general, it's very difficult to do that. So learning probabilistic inference, learning these algorithmic tasks, but sometimes we can actually make this work. So there are some works that actually have successfully managed to extrapolate, say, to larger graphs. But with other neural networks, this is often very, very difficult, which is kind of a little bit puzzling, because after all, like, these MLPs are just a building block of our graph neural networks. So it's again really the question, under what conditions can I actually say that this neural network will successfully extrapolate to other, like, out of distribution data? And to think about that, I would like to go back to this viewpoint of a graph neural network as a structured arrangement of little learnable modules. And we'll first look at a module, and then we look at the big network, like, or the interplay of these modules in the big network. So let's look at one of these modules, basically one aggregation function. The learnable part is the MLP. So what does an MLP do if you give it data out of distribution? So here are some very simple experiments. So this is averages over MLPs of different sizes. So we had, like, simple, relatively low dimensional quadratic function, cosine function, square root, linear, and L1 norm. And you see that basically you get very large errors for all the nonlinear functions, and for the linear or piecewise linear function, it kind of partially works in some cases, and in some cases it doesn't. So there's something to do with the linearity, but now I'd like to just think about, can we understand this a bit better, what's happening here? So one important piece is that this was a ReLu network, because often people use ReLu networks for that. So let's just look at it like at a very simple setting, one dimension. So let's say I have a one-dimensional input. This is just my sine function, and I look at training data in this blue box. And then I just look at what does my neural network do out of distribution. So how does it extrapolate? And what you can see in this case, it actually just sort of extrapolates, like, directionally linearly. Yes, you go away from the training data, you get these linear functions. Now, thinking that this network uses ReLus, which are piecewise linear functions, that's maybe not so surprising, but it really concentrates all the nonlinearity where the training data is. And this happens also for higher dimensional, like in higher dimensions. So what you get is you don't get like a general linear function, but as you go away, like in each direction, you essentially get a linear function. So that's sort of the low dimensional plot of the function. And you can also prove this. So here's a theorem that says exactly this. So this says if you train your ReLu MLP with gradient descent, if you go away from the training data in an array, basically very quickly your function will just approach a linear function. So this is a simplified proof with like a 2-layer network and proved in the neural tangent kernel setting. But you see actually empirically this holds more generally too. So this is something to keep in mind, essentially, that as you go away from your training data, this learnable part really just implements some kind of linear function, pieces of linear functions. So that's what we'll have to work with. How do you prove this? So here's just the idea of the proof. That's where the training algorithm comes in. So we had the architecture, now comes the training algorithm. So you look at the neural tangent kernel. So that's an approximation of the neural network where you basically look at the tangents at initialization, and then it essentially resembles some kind of kernel method. So you got a closed form solution, and you know the solution with gradient descent will be a min norm function in that function space corresponding to that kernel, to that neural tangent kernel. And then you just look at what do these functions actually look like, and that's essentially what you see. So basically the message is directionally linear extrapolation. Now, the other thing is that, well, okay, maybe we have to work with linear functions, but now if we want to learn a linear function, we still actually have a ReLu network, which can implement potentially much more than a linear function. So to really learn the right linear function, we actually need enough information in the data, meaning sort of enough support in all directions to learn that we sort of should be flat in all directions. So that what the plot here shows is that the data had only support in one direction. So you only sort of learn the right linear function in one direction, but not the other direction. So that's what we have to now sort of take home for our big network. We can only will be able to have sort of directionally linear functions in our aggregation functions, and we need enough support in the training data geometry. So one more comment is, when would sort of my aggregation function be out of distribution? So I know for the big network, it's maybe a graph that's larger, a graph that has different degree distributions. So for example, if you have a different degree, then the input to the aggregation may actually become larger than it is, so out of range. If your node features are larger, they're out of range, etc. So basically a graph with a different structure easily probably would take it out of distribution at some point. So now let's, keeping those two things in mind, let's go back to our graph neural network and see what would this mean for our graph neural network. And to illustrate this, let's go back to my running example, the shortest path algorithm. So this is again the sort of piece of the algorithm that we want to implement, this min over the neighbors. Now I can actually implement this with my MLP in the sum by universal approximation, but to implement a minimum with a sum and a nonlinear function, I need to really learn a nonlinear function with my MLP. And this means once I go out of distribution, it's going to just be a linear function. Now, if we look at the literature where people actually manage to have successful extrapolation with graph nets, they actually don't use a sum aggregation. They use a min or a max aggregation by architecture search and found that that actually works better. Now, if you look, if you already have the min instead of the sum to do the aggregation over the neighbors, then you really only need to learn a linear function because the minimum is already there. You really just need to sort of sum up the edge weight and the node feature. So that's much easier. And that would supposedly work better. And I'll show you in the next slide that it actually does. So this gives us a modification of our notion of this algorithmic alignment. So what we said for generalization, what we need is that the network can mimic the target algorithm by a small number of simple function, easy to learn function. So here really what we may actually need is that these functions are not only easy to learn, but they're actually linear. So we call this a linear algorithmic alignment. And this is the difference between extrapolation and interpolation. For interpolation, you can have nonlinear functions. For extrapolation, you would actually need nonlinear linear functions for extrapolation to work. So here's one empirical result on this, again, for shortest path. So we have two different networks. One uses the min aggregation and one uses the sum aggregation. So the gray one has to learn a nonlinear function and the pink one has to learn a linear function in its aggregations. And now you see that for interpolation on the right-hand side here, it doesn't really matter. So both of them get small error, both of them are able to generalize fine. But when you look at extrapolation, that's when you see the difference. So extrapolation, you are fine with a linear function, but you're not fine with a nonlinear function. So that's sort of where this linear extrapolation of the ReLus kicks in. So that's sort of in the extrapolation setting, we see the difference. In the interpolation setting, both generalize fine. So what does this mean if we want to design neural networks for other types of tasks? Well, it's in some sense a bad news because it's pretty limiting that if your data really looks very different in structure, well, you have to restrict your model class a lot. And that basically means that what your learnable parts have to be linear. Now, if the target function is actually nonlinear, how do you achieve that to model that function? So basically, the way we achieved it here is that we put in prior knowledge in the architecture design. So either in the architecture design, or we basically change the input in a way that, so we change the input features in a way that the function we need to learn is more linear. So this seems restrictive, but if you actually look at some of the results in the literature that achieved successful extrapolation, many of them actually do have very specialized nonlinearities that put in prior knowledge already. So the actual learnable part, again, in these networks is much more linear because they have some library, because they use sort of this exponent log or learning physics laws, essentially also they implemented a lot of prior knowledge in this. So in those cases, you could actually extrapolate. So what does it mean for learning for optimization? Essentially, if you have knowledge about successful optimization routines, it's probably useful to put it in. The other option is to change your input representation. So this is for sort of forecasting these physical systems. So here the task is to predict where the planets will go. These are planets. And now predicting the next position as a function of the position of the other planets and their velocities is a very nonlinear function. But if you change the representation, if you do sort of 1 over the distances, etc., this becomes more linear and it actually is easier to extrapolate with that. So that's sort of what these plots are showing. Now you could do this either by prior knowledge, or maybe there's a way to get at the same goal via representation learning and pre-training, because that sort of puts more data within distribution, and you have seen some kind of data like that before. So let me just make one more comment. I said, well, the data support also matters. So here are some empirical results on that. If we train on just very specific classes of graphs and look at how do they do in general graphs, you get very different performance. And this is not surprising because some of those classes of graphs actually have like all the same degrees, for example, they look very regular or so, or a path. There's not much to say, like in a path, you could just predict shortest path by just counting the number of nodes or so. So it's very hard to figure out the correct function then. So in limited cases, we also have theoretical results that make this very explicit. So if you, for example, look at the task of learning the maximum degree, so even if you have this linear algorithmic alignment and your architecture satisfies all those constraints that I talked about, you do have additional constraints on the data. So in this case, what this constraint essentially says that in your data set, there should be enough variety in the minimum and maximum degrees in the graphs that you have and how they occur in your data set. So that's essentially what this condition says. So this goes back to this to the fact that you actually need sort of enough directional support to learn the correct ReLu functions. There has been other work on extrapolation in graph neural network. Essentially, what all of these works say is either you need sort of enough similarity between your like training and test distributions that they're essentially of the same structure. So that's the first type of works. And then you can extrapolate, or you have these strong conditions on the architecture under which you can extrapolate. So that's the second type of work and also the work that I showed you. So in summary, we talked about 2 types of questions in learning with graph neural networks for algorithms if you want to learn an algorithm or even a part of an algorithm. The first thing was if you want to generalize, what really helps is if your neural network structure already implements some prior knowledge about what this algorithm would look like. to get the right inductive biases, essentially. That reduces the sample complexity. And trying to formalize this. So what this algorithmic alignment does is it tries to formalize this. The second one is about extrapolation, where we don't only need sort of a match of the architectural structure, but really also the nonlinearities matter a lot. So with that, I'll stop here and thank you for your attention.
Thank you so much, Stefanie. Well, what a great great talk. You always have these intuitions about the inductive biases that you want to incorporate into the modeling of your networks, but here we actually see them being formalized and in a very targeted and nice way. If there are any questions, please feel free to unmute yourself and ask. So maybe I'll start.
Maybe I'll start. Thanks, Stefanie, for the great talk. So you prefaced by saying that when it comes to optimization on graphs, you were going to mainly use some simple problems like shortest path, max degrees, etc. So I can see that even in those cases, there might be some benefit to learning something, because maybe the shortest path is just a module in a bigger architecture, which involves other learnable components, which also need gradient descent. So even if you had Dijkstra's or Bellman-Ford, you couldn't maybe differentiate through it. So you would plug in something which approximates a shortest path algorithm. But my question is, are there any barriers to applying the same kind of, say, sample complexity analysis, but for problems which are, say, NP hard, right? So say you're doing, some kind of vertex covering or sensor placement or etc., where actually there is no, polynomial iterative procedure like the one you have for shortest path. Maybe there's something approximate. So if maybe for sensor placement, there's the greedy algorithm from submodular optimization, which does something reasonable. Is there anything in the kind of analysis that you showed that relies on the exactness of the procedure, such that it makes it not applicable to like approximation algorithms, or is it independent of that?
Yeah, so here this is really for exact tasks. People have, of course, also tried to learn approximation algorithms. So there, I would think, so you could maybe say you have some alignment with some kind of approximation algorithm, whatever it may be. What would probably change a bit is the learning analysis, because that assumes you can, it doesn't assume that you solve the task directly, but the feedback you get, of course, is for the correct task. But I think you could think about an alignment with essentially an approximation algorithm. So the same kinds of tendencies would hold, I would think. I haven't tried it empirically, but I would expect that the same kinds of patterns would hold. So I think you could generalize this analysis. We didn't do it, but where potentially you'd have to be careful is when you think about the loss, what is exactly the loss function, and how these gradients, where do they take you? What are you actually learning? But I would think it's possible to generalize it to that setting too.
Mm-hmm. Because right now the loss function, for example, for shortest path is just something like mean squared error, something differentiable in the path length or something like that. So you're just trying to minimize the error to that, right? Yeah.
So right now it's a little bit of sort of an unnatural function that people don't have used. Yes, it's basically just the differential. You learn it essentially like a regression task.
Okay, so I can see how that can be problematic for maybe an approximation. That might be an issue.
But possibly if you actually use the objective function instead, and then you may still get some, yeah. I'm not exactly sure, but maybe you, I think the general tendencies definitely hold that basically if your architecture has a structure that already is close to some algorithmic technique, even if you don't like implement the full details of it, like the broad structure, like whether it's a greedy algorithm or some kind of message passing algorithm or something, that would, I would be surprised if that doesn't help to some algorithmic structure that would be successful for that problem, or like for certain instances of that problem even. For the full theoretical analysis, like I'd have to think through it where it holds. But I think the same viewpoint of the like thinking about it as a structured arrangement of learnable parts, and then you look at what do these parts do, what would they actually implement, and like how would that say extrapolate, and what would that mean for your main task, etc. Those kinds of things you could definitely do.
Makes sense. Thank you.